Today we're doing radioactive half-life. So write down the title, radioactive half-life. If I throw 2 pens into the air, 2 pens, what's the probability that generally in the northern direction, so that half of the room, how many of the 2 pens are going to point in that direction? 50-50. So one of them will point that way and one will point in the southerly direction. So we were pretty much right. One went that way, one went that way. What if I throw 12 pens? 6 will point in that general southerly direction and 6 will go in the northerly direction. 6 pointing this way. Look at that. The experiment was right. Does it always happen that way? No. Okay, so this is the same for radioactive half-life. So, in case you didn't know this already, each type of atom has a type approximate half-life. Okay, so each type of element. So lead's half-life is different to uranium's half-life, okay? And they span different time spans. So a half-life, in case you didn't know, is the time taken for half of the radioactive atoms in a sample. So I used pens, but let's imagine we're sampling atoms instead. It takes the time for half of those atoms to decay into a different type of atom. For example, a nitrogen sample, so a sample of nitrogen, after 10 minutes, 10,000 nitrogen, N13 isotope nitrogen goes from 10,000 of those to 5,000 nitrogen. Okay, it's undergone a decay. What happened to the other 5,000 nitrogen? They decayed into not nitrogen. Very good. So you got 5,000 of the 10,000 left that are nitrogen. The other 5,000 have decayed. And that is the half-life of nitrogen because half of the atoms have decayed in 10 minutes. It's impossible to predict this though because there's not an exact amount for every nitrogen atom. There's not an exact amount for every lead atom or whatever the atom type is. So it's all up to probability statistics, okay? So it goes down like this curve you can see on the screen. So this is a nitrogen curve. It's gone down after 10 minutes to 5,000. After another 10 minutes, what is the amount of nitrogen now? Now it's 2,500. All right, let's do a question. Have a go. So we've got iodine, 131. It has a half-life of 8 days. Write it down. Half-life, T subscript half, 8 days. What is this? What is this number? N0, correct. At a particular time, how many atoms of iodine are present after 40 days? So the time that's gone is 40 days. So first step. Correct, which is how many half-lives? 5 half-lives. Good job. Now we need to find how many atoms. That's what we're trying to do. So we're using this equation. This gives us how many atoms, which is the original atoms, times by half to the number of half-lives. So we've got 3.0 times 10 to the 18 times a half to the power of 5. You get out your trusty calculator. And hopefully you would have got that answer too. Oh, don't forget approximately equal sign. And don't forget some words. So what's this number represent? So it wants us to find how long it takes. So it wants eventually to get the time it takes. But first we need to find n, little n. So we need to use that equation I just gave you. What's the equation I just gave you? Log base 10. Very good. So we sub it in. What's the thing that it eventually gets to? What's the number it eventually gets to? Reduced to? What is the one that it starts on? And then, yeah. So you type it all into your calculator. Second 10 to the power of 6 divided by 3, do a bracket, 3 times second 10 to the power of 18, bracket, nope, bracket, second bracket, and then divided by log 0.5. Enter. 41.4. Okay, so that's the number of half-lives. The number of half-lives, time elapsed. So the time we're trying to find divided by the half-life time. So to get t by itself, you do, or the time elapsed, you do the number n times by whatever the half-life is, which is 8. So yeah, correct, we just calculated that, and the question tells us it's 8 days. I suggest using the full decimal that you got. So I would do times by 8. And yes, there it is. Is there any questions?